Just give me one. Right. So we know that in a computer, we'll have a microprocessor, and this microprocessor is going to have multiple units. So this is the standard ALU unit. Let me switch to the ALU unit, and there are multiple other units. Um, there are multiple segment registers as well: the code segment, the stack segment, the data segment, and the EXO segment. Right? When we write a program, that program goes and sits inside a RAM. The RAM is going to have uh, different memory segments that'll be pointed by the segment registers. We also established that CS and IP combination is going to execute an application. When the processors got advanced, we switched to 80386. This was the first completely supporting microprocessor with uh, multiprocessor support added in the processor. The way it is done is that it is going to create special location, and those location will be marked with special permission. For 00, for example, is going to be code that could be executed. So the rest of these bits, they're going to point to the start and end of the code segment. So this particular segment is going to become code pointed by this. There's a special word for this, right? When the operating system chooses that it wants to switch from processor 1 to process 2 to process 3, it is going to come and modify the internal state of the processor, and it is going to change the CS and IP register values. But then just changing CS and IP is not going to be enough, right? When when the operating system switches from one process to another, there is a lot of context switching that needs to happen. And this context switching is special data that is going to restore the process back to its original state. Now, this context can be extremely big depending on the size of the application and what data this application is interacting with. And then these are processes. So to avoid the overhead of having these multiple processes, operating system came up with another concept, and that concept is called threads. Now, a thread is a lot like process, but the footprint that they have compared to this process context, there is something called as thread context. I'm going to represent it with CTX. A thread context is a lot smaller, and a thread has a dual intention. So if you're working, say, on a forms application, right, and then this forms application is supposed to connect to the internet and extract out, say, a very large file, right? If you are running it as a parallel code that the window is loaded, and then there is a download function that you are calling from on some object, then until this entire 1 GB of data is downloaded, this application is going to go in a not responding mode, right? That happens because the entire UI is going to wait for this download function to finish, right? Threads, they have a different purpose. So within the context of a process, a thread is going to create multiple independent executable paths, and those paths, they are going to take care of different activities. So each application, it is going to have at least one thread, and that's called the main thread. So whether you create it or not, the operating system is going to give you at least one thread to begin with. When you are in the .NET world, there is another thread that you're going to get, and that thread is called the garbage collection, right? We already established that the RAM is going to have multiple segments to it, and one of those segments is going to be the data segment. Another segment, if we can talk about that, is going to be the stack segment. The stack always starts at the bottom and works its way up towards the data segment. Now, when we declare a variable like this, where integer I is assigned to 10, because this is a reference type, it is going to go and sit inside the stack here like this. But then when we declare an object of, say, a customer using new customer, there are two things that's going to happen. The customer itself is going to be a very complex object with strings and integers and float and other structures inside them, right? This is something that you do not create on stack, but this object objcx itself is going to sit over here, and it's going to take a very basic amount of memory, which is about where is the address of this particular memory location. And the memory for the object itself is going to be given from a data segment. Now, this is called a managed memory, right? And the .NET CLR kind of keeps track of how many objects like objcx, how many objects are referring to this particular member. In the instances when no object is pointing to this memory location, the garbage collection unit is going to wake up, and it's going to free up this memory for other applications, right? Your application is going to have multiple resources. Memory is one of the resources, and C# only takes care of that one type of resource. All the other resources of that your application creates, such as the network operation and the disk operation, is something that you will have to take care of yourselves, right? So when you are working in an application that has multiple responsibilities, such as deriving a UI and probably connecting to the internet, you are going to run into two types of operations. One that is CPU heavy, and two that is IO heavy, right? An IO heavy application is downloading 1 GB of file from the internet, or probably saving 10 MB of data on the hard drive. Because hard drive is a slow resource, right? It is going to take a while before this data is written on the drive. Internet is even slower device, a slower has slower frequency compared to the CPU itself. The CPU is running at about 2 to 3 gigahertz. Right. The internet is downloading data at, if you have like amazing internet, at 100 Mbps. Right. The hard drive probably is writing something at the pace of, say, 4 megabyte or probably more, depending on what kind of hard drive you got. But then these speeds, they are nothing compared to what the CPU has to offer. So when you are performing an operation that is heavy on IO, your application is going to have to wait till this thing finishes. And then this waiting is not a good strategy because our CPU is wasting a lot of cycles. So what we do is we create multiple threads, and these threads, they're going to perform these operations for you in the background. Right. So .NET offers creation of threads through multiple APIs, and we're going to take a look at them. So with that, let's jump into Visual Studio. And I'm going to get rid of this code. So I've already gone ahead and written the boilerplate code. This is the main program, the app class, and then the app class is going to have a public void run method that we are calling from the main function. Now, the way to create a thread is you declare a variable, say thread, T for thread, and you create an object of new thread, and notice that it has at least 4 overloads. We are going to use we're going to pass this thread a function name, and we're going to call it. OK, let's go ahead and check this example out. I'm going to start with the for loop, and we're going to run this loop for about 5 seconds. In this loop, we're going to call thread.sleep statement, and we're going to pass it, say, 3000. Right, and over here I'm going to type the value of I. Now if I hit Control F5, all right, this program is going to start here, and every 3 seconds it is going to print a value on the screen. It's going to go all the way up to 4, and that's when the program is going to terminate. All right, but then notice that there was a slight delay, exactly 3 seconds, because of the statement here called thread.sleep. So what this does is it stops the execution of the current thread, of the executing thread, for 3 seconds, and when those 3 seconds are over, the rest of the application it kind of starts. Right. Right. All right. So this is the easiest way that you can demonstrate that there is something in execution that can be stopped. So let's go ahead and comment this code out, and we're going to create a thread that is going to do something more meaningful. I'm going to create the thread object like this, and I'm going to pass it new thread, and out of these 4 overloads, I'm going to choose the thread start option. It requires an object of type thread start. So let's go ahead and create that object first. So I'm going to call it thread start as new thread start. And if you look at the definition of this, it is taking a function called void. Let's press F12 here. And then notice that this is of type delegate, right? A delegate is going to call another function for you. So what we're going to do here is we're going to mention a function name that is going to do some meaningful activity for us. So let's go ahead and call it square numbers, and we're going to close it at this. And thread start goes here. Now this function does not exist at the moment, so I'm going to hit Control dot and generate a method called square numbers. Now notice that this function is taking a void parameter. So if I hit Control dot and you let Visual Studio create that function, it is going to create a function that matches the parameter type that it requires. Now I'm going to run a for loop here, and that for loop is going to run for, say, 5 elements. And over here I'm going to say $, then I'm going to print value of I, and then square of I is I into I. But then in between these activities, I'm going to take a quick pause with thread.sleep of, say, 2 seconds. All right, so this thread is okay. This is 2 milliseconds. Let's bump it up to, say, at least 1 second. Right now that we have a thread start and thread, we'll have to figure out a way of kickstarting this particular thread. The way I'm going to do that is by calling a function called start on this. Right, the start function is going to spin up. It's going to spin up a new thread. So there's a UI thread that is already doing something. There's a garbage collection thread that you are not going to see until you do something, some tricky stuff. And then we have created a new thread that is going to square the numbers. it is going to print those 5 values on the screen, and the execution is going to happen parallelly. The t.start function is going to trigger the beginning of this particular function. So let's go ahead and run that. I'm going to hit Control F5 and notice that with an interval of 1 second, this count of I is increasing and we are printing the square of the number on the screen. Now, just to witness that this was a different thread, we are going to give me 1 second. We're going to print something after this line here. I'm going to say console.writeLine inside run function. Now, if I hit Control F5 and see this, notice that inside run function logically does not align. Makes sense? Because with this statement, we are entering into this particular function. This function is performing something at a slow rate. While this function was executing, we saw this output printed on the screen, which indicates that this particular function is running in its own thread, and this is a parallel execution, which is happening at its own pace. Make sense? Now we can go on creating multiple threads like this. So let's go ahead and do that next. I'm going to call it thread 2. I'm going to do thread 2.start. I'm not sure if the same object is fine, but let's go ahead and try that. And then over here, I would want to have some form of indication that it's a different thread where this is happening. And then that information is available on the constant static object. So these are static object, current thread, and current thread is going to have a managed thread ID. Right? The reason it is called managed thread is because the CLR is kind of kicking in, and the CLR is controlling these threads and their execution for us. So I'm not going to put it over here. I'm going to put it alongside this particular variable over here. All right. So it is thread and then the thread ID and the value of I and the square of that value. Now, if I run this application, you're going to see that there are two IDs, thread 5 and thread 4. Thread 5 is doing it from 0 to 4, and thread 5 is also doing it from 0 to 4. And while those threads were starting up, the control had already gone to the main thread and it printed inside a run function. And the other two threads, they kind of continued their way to execution, right? Both the threads processed the same execution, and it is through this execution that we were able to see two sets of output, one for each individual set of thread. Right? Now, let's go ahead and create a problem between these two threads. So far, we had been using the value of I, which was local to the thread itself. Now, we're going to change that a little. We're going to declare member I outside at the class level. So I'm going to declare I over here like this. I'm going to assign I to 0. And now if I run the application, all right, notice that a couple of numbers are missing. Right, so it started with 0. 0 square is 0. Then we saw 1, but then we did not see 2 ones the way we saw 2 zeros. Ideally, we should have seen 2 ones. I mean, it was like 5 elements for both the sources. The loop should have run 5 times for both the threads, but then that is not going to happen. And the reason is this variable I here is a shared location. So if we go back to the whiteboard, what we have essentially done, we have created a copy. So this blue is, say, thread number 4, and the green is, say, thread number 5. We have added a variable that is shared between these two threads. When you have a shared memory location defined in this way, the effect of one is going to get reflected in the other. So when we do I++ in the for loop over here, right, this I++ is affecting the execution of the other thread as well, right? And it is leaving our system in an inconsistent state. You keep running this thing. If you drop this count to, let's go ahead and create another thread. Let's do thread 3. And if I hit Control F5, right, there are crazy things that are going to happen, right? So it is 1, 2, 3, 4. Right? Each thread did something for itself, and then all three threads, they started with 0. Right? What we are observing in technical terms is called as a race condition. A race condition is when there are multiple threads that are competing for the same resource. Right? This is thread 6. They are all competing for the same resource, and they are leaving the system in an inconsistent state. The objective is that when one thread is in execution, we don't want it to be impacted by another thread. And there are multiple strategies with it. The first strategy is introducing some synchronization variables. So there's something called as auto reset event, and I'm going to call it, say, okay, I cannot use the word event, but then let's just call it counter, right? And I'll have to initialize this variable like so, and then it can take one of two Boolean values. So true is going to ensure that the thread is going to get started automatically. And because it is going to cause some confusion, let's go ahead and create two functions. So far we were doing square. Let's go ahead and do a cube as well. And then over here, we're going to change this value to iCube. And let's assign this to the second thread that we are creating. So we're going to require a new thread start object. So I'm going to say var thread start assigned to new thread start. And over here, I'm going to pass cube numbers, right? And then thread start, I'm going to call it cube, and I'm going to call this as square. So this is going to cube it, this is going to square it, and I'm going to delete thread number 3. Now, to synchronize execution between two threads, we're going to use the value of this counter. So as soon as we enter this function, we're going to say counter dot wait 1, and we're going to say counter dot set. We're going to do the same change in the cube function as well. All right, let's go ahead and see this code without these synchronization statements. We are still going to see an overlap between these two processes, that sometimes you're going to see a cube, sometimes you're going to see a square. So 4 is getting squared, 3 is getting cubed, and 2 is getting squared. 1, I'm not sure. Because it is thread 5, I think it is cube, right? Because thread 5 is doing cube, right? So these two threads, they are executing separate functions in their own separate context. Now we're going to introduce a counter dot wait 1, and let's just watch the effect of this wait 1 over here, like so. When I set it, I'm going to increase this from 5 to say 10. And once again, I'm going to say wait 1, and over here, I'm going to say dot set. I'm going to hit Control F5. Let's see the output, and we're going to talk about the effect. Let's do one quick thing. I'm going to drop this back to 5. I'm going to set the value of I back to 0 here. And now let's run it. So after 1 second, thread 5 is taking precedence and it is doing cube. And then thread 4 starts with the value of 1 again. Now, there is no set rule for this. This time, thread 4 has started first. It is doing all these squares. And then thread 5 did not get a turn at all. Because thread 4 is also supposed to set the value of I to 0. So thread 4 ran this time again. First, it is the square thread, and then thread 5 started with 0 again, and it is doing the cube. What happens is when you put a statement like this, wait 1, and you create an auto reset event, the auto reset event is going to provide synchronization between different threads. Because we have set it true, it is going to say that, hey, whichever thread runs into this statement, wait 1, they're going to ignore it, right? Because they have ignored it, they will resume their execution and they will complete their flow. And when they set it, this wait 1 is going to say that, hey, anybody who is also doing synchronization using this particular object, you all have to wait. So whichever thread executes this code first, it gets the precedence, and all the other threads that are in the queue, they are going to start waiting. So just to demonstrate the purpose, I'm going to repeat this code, and instead of cube, I'm going to say increment number, and for increment, I'm going to change this cube condition to +1. Sorry. And then I'm going to create a new thread. I'm going to call this increment, and I'm going to call the increment function over here like this. Increment numbers. This becomes thread 3. This becomes thread 3. And once again, I'm going to, as the last line, I'm going to print inside the run function. Guys, I'm going to take a quick break, and I'm going to join back real soon. All right, guys, I'm back. Are you all there?
Yes, sir.
Yes, yes.
Sure. Sorry about that. And a quick announcement that my Wednesday meetings, they are getting very tricky. So probably starting next Wednesday, we can start session at 9:30 around this time, or we can cancel our Wednesday session and switch everything to, say, Saturday. So I'm going to evaluate these options and I'm going to let you know. All right. So let's get started. I'm going to share my screen. All right, so before we went on break, we saw that a thread is an independently executable unit that the processor creates, and it gets managed inside the context of a process. The reason we create threads is because threads, they have a smaller context. Switching between processes like this is going to take a heavy toll on the CPU, and as the number of processes increase, this switching becomes so much of work for the operating system and the CPU that each process is going to get very little time from the CPU itself. And that's why we have threads. Threads solve this problem number one of switching between different heavy contexts, because the context of the thread itself is very small. It generally restricts, roughly speaking, to the data that it is dealing with and the data that it has access to. There is at least one thread that your application create. I would say two. That one is the main thread itself, and the second is the garbage collection thread. Garbage collection thread is going to run every few minutes, and it is going to free up the memory to which there are no references available. We can create threads using the thread systems.threading namespace assembly and calling a new function on an object called thread itself. Now, there are multiple overloads that this function takes. One overload is that you create a thread start object and you pass it a function name. This thread start object with this function name, when passed to the thread class, it is going to give you an instance of thread, and you can call thread.start, and it's going to run that thread for you. Before we went on break, we saw another problem that when two threads, they are sharing a variable which is common, it is going to run into race condition. Race conditions occur when two threads try to access the same memory location, and the effect of these two threads execution is unpredictable. Like depending on which thread goes inside the CPU and runs the update code first, the effect is going to leave the application or the output in an inconsistent or an inconsistent state, which you cannot predict. Then we found a mechanism through one technique, which is called auto reset event. There are multiple other techniques, such as manual reset event. So this is the opposite of auto reset event. It is called manual reset event. There is another event called semaphores. So using semaphore, you can provide synchronization between multiple threads, but we are not going to look at all of them. We are only going to restrict ourselves to the auto reset event. I encourage you to go and read about different type of data thread synchronization techniques. So we're going to create a variable called counter. This is not going to count anything. This is only the reset event. We started this with the true value. So when this is true value, the wait one statement is going to fall through. It's going to come and check the value of this particular counter. Because it is true, it is going to set it to false. And when that gets to false, all the other threads that are waiting on that counter, they're going to continue waiting. So out of these three statements, only one statement is going to get through, and the other two, they're going to get blocked. They're going to get unblocked when we run a set function on the auto reset event object. This set function is going to set it back to true. When this sets to true, out of these two waiting, any one is going to pick up. You cannot control, you cannot dictate, right? It is the operating system, it is the flow execution that is going to come and let one of these two codes take control, resume. It is going to resume, and the other one is going to go in waiting again. When that happens, the other function is going to resume, it's going to run the set function again. When this sets, the only waiting thread, the third thread, is going to pick up and it's going to resume its activity. This is how it is going to be, but then the only thing that we don't have control over is which of these threads is going to get executed. Right. So before we went on break, we added this increment function. Let's go ahead and run this code. And once again, right, here's the output. So it started with probably the cube function. Then it started with probably the once again the cube function. I think I made some mistake. And this is the square function. I think I'm not calling the right function at the right spot. So let me close out this, copy this increment numbers, and increment numbers is here. Thread start increment. I have to pass this object to the third thread. Now if I run it, right, this time it is thread 5, which is going to do cube. When that completes, it picks thread 4 kicked in, and thread 4 is probably square, and then the increment thread that is taking over. Right, just to cut these things very close, you can go ahead and combine these thread.start statement like this. Right. So because they are like cutting so close, we won't know which thread is going to take over or going to get the first turn. So it's once again thread 4. And I hope you notice that there is only one thread that's getting executed, and the other threads, they will have to wait till the execution completes. So I'm going to close out of this, and this is threads for you. This is how you create multiple threads. This is how you synchronize these threads. All right, let me. I wanted to show you at least one example. There is something called as timer. And then if you remember from our JavaScript session, there is something called as set interval. Set interval is going to execute one function every few seconds based on the interval that you have set it to. .NET has something very similar, and it is called timer. So if you want to execute an operation every few seconds, you should implement a timer. And just going to copy the code from the internet. I'm going to paste it here. So let's go ahead and comment this code out as well. And then over here, I'm going to paste this code. So there's a class called timer state. If I hit control dot, we'll have to create that class ourselves. So I'm going to create it right here. So a timer state has one public member called counter. So with this class added, we're going to get the timer object. So let's go ahead and declare that as well. I'm going to assign var timer equal to new. And the timer task is callback function. So let's go ahead and hit F12 on timer callback and look at what this is expecting. So this is expecting a state. And then let's read through the description. It says represents the method that handles call from system.threading.timer. Now, this object is supposed to take care of what you want to do when the timer expires. Right? So this has to be a function. So let's go ahead and create that function. I'm going to hit control dot, and it is giving us two options: generate a method and generate a variable. We're going to just choose the method option, and the method is added here for us. When this function executes, we are simply going to say console.writeLine, and we're going to say probably date time that now, like so. And the state itself, you're going to say, we're going to call this, instead of state, we're going to call this timer state, and this object is of this data type. All right, always. So we're going to go ahead and do a typecasting of the state object that the callback gave us as the timer state. And now we can go ahead and increment the value of this particular timer state, this object dot counter, and we're going to do plus plus. Okay, now I'm going to ignore this. I'm going to say thread dot sleep, and I'm going to give 1 second delay. So let's run through this code one more time. We have created an object called timer state. Timer state has a public member called counter, right? Then to create a timer, the timer itself, which is going to expire every 1 second, we are going to call this special class. I'm going to hit F12 on this and then look through the description of this timer class. Provides a mechanism for executing a method on a thread pool thread at specified interval. Okay, you want to run something at specified interval, and it's going to take multiple parameters, but then all these parameters, they are going to be about a callback. Okay, so we have already created the callback over here with this timer task. So new timer callback, timer task, it is a function. This function is guaranteed to get executed when the timer expires in this particular object. The second is the state itself. The state is the timer object that we want to pass. Right? So because we are creating this timer object here, this timer task is going to take the same object, right? And then the due time is the interval in which you are going to expire this, and the period is how many times it is going to get executed. So let's go ahead and run this. There is one loophole that I have left in this code, which I'm going to show you a little later. But every 2 seconds, right, it is going to increment the counter, and I wanted to print the counter value as well. I forgot doing that, so let's do that now. All right, so every 2 seconds, it is increment the value of that counter. I'm going to hit Control C and stop the execution of this. Or we have something in our code already. So it is checking if the counter value is less than or equal to 10. It is going to keep waiting. And when this happens, this is going to dispose of the timer. So let's reduce this value to 5 and run the program again. So when this value reaches 5, the while loop is going to kick in, is going to end, and it is going to dispose the timer, and it is going to print something. So when the value became 6, it said done, and done is printed over here. All right. So the timer after the dispose function call is kind of expired. It started after 1 second. It was running every 2 seconds, and it was executing this function. All right. So when those 2 seconds were over, it was calling this function. Right. And then inside this function, we are just incrementing the counter value. The loophole that I said I left is this particular statement here. Right. When you are inside a function that is created specifically for thread, right, you cannot go about modifying that value without some form of locking on it. So the way we're going to create that lock is we're going to say obj object timer lock, and I'm going to assign a new object to it. This object is used by threads to ensure that if there are multiple threads that are executing this code, they are not going to run into each other, right? And only one thread is going to access this critical section. So in C#, there is a statement called lock. Everything that you put inside the lock statement is thread safe. All the other threads, they're going to wait outside this block until this kind of completes. When this completes, it is going to release. The next thread is going to come inside and increment this value. With that said, there are easier ways of doing this. Because we are doing a simple operation, we can switch to another implementation, and it is called interlogged. And then you pass it a value called increment, and then you can pass it the variable itself, and you can get rid of this code. I'm going to put a semicolon here. And then this has to be a reference variable. So ref is a trick of converting a value type to a reference type. And this reference type is going to go inside and come out modified. Right. So if I run this program again, it is going to run for 5 seconds, and it is going to the while loop is going to end, and our application is going to complete this. Make sense? So what we saw here is if you have something that you want to do every few seconds, you can create an instance of a timer, right? And this timer will run this particular, it would trigger this particular function every few seconds, and you can take care of timer based activities. All right. All right, so that completes our discussion on threads. Because we are like reaching end of time, I'm going to start the topic of garbage collection. Now, Now, a .NET process is going to have multiple sections of code. So this is going to be multiple data segments of the memory. This is the code segment. This is the data segment, right? Inside data segment, the uh, the CLR is going to divide this section into 3 types of memories. When we create a new reference type object, say a customer, right? A customer is going to get declared at 2 places. The variable C that is going to store the value of customer itself is going to get a spot of say 4 to 10 bytes inside the stack. These 4 to 10 bytes, they are going to store multiple information like where C is pointing. So the first instance itself is going to be uh, the location in heap or the location in the managed memory itself. The second information is going to be how many members it has, right? So suppose if the customer has a name, an ID, and email, right? The type of these things, roughly speaking, they are also going to be part of this particular memory section, right? In C programming, there is a operator. It is called size of. If you pass it a variable like I, or if you pass it a data type like integer, it is going to give you the size of that particular data type. In C sharp, you don't have size of operator. And the reason is C sharp kind of manages the memory for these objects inside for you. And it kind of keeps it the decision of how many bytes it wants to allocate. It kind of keeps it to itself. And that's why there is no size of operator. You will never be, okay, not in an easy way, you will be able to determine as to how much memory is given to you unless you take a dump of a program of an executable in execution, which is already in memory. You run it through special commands. Let me show you that command. So I am going to launch the task manager. And then inside this task manager, if I pick up some random process, such as say AnyDesk, and say create dump file, this dump file is going to result. This has been created at this location. Okay, so let me go ahead and copy this location. Modified. All right. So in the dump file, this is what we are seeing, that there is a file of 85 MB that is created. These 85 MBs, they represent what the code segment, the data segment, and all the other memory that has been given to that program, AnyDesk, looks like when we clicked on this button, create dump file. Now, there are special softwares in which you can open this dump file. And if you know the command of that software, you will be able to see how many threads it had and how much memory it was using and information like that. This comes in handy when a customer complains that the application is crashing out of order. The application is performing very slow. It is taking a lot of RAM. So I've closed the task manager. Let me bring that up once again. So inside this performance tag, when you are building server grade application, you are going to constantly monitor the CPU, the memory, and these two things, they are going to decide what is the performance of the application, right? I'm consuming like 15 GBs of around 13 GBs of my total 16 GBs of RAM, and the available is 2.5 GBs, right? There are other detailed information that you can get, that what these GPUs are doing, what is the quality of the internet, and there are other places where you can see thread related information as well. So in applications, when an application is not performing, or you would want to do some form of special analysis on these programs, you generate those dump files. Through dump files, you can get the exact idea of what was present in the code and what was present in the data. Now, the reason I was telling you that is because there is no easy way of identifying what your variable looks like. All you know is that it definitely points to some other location inside heap. Now, the name garbage collection, or the short for it, GC, is kind of an incorrect terminology. GC is not doing cleanup afterward. GC's main functionality is to cater to the new requests that are coming in. Now, when you put a new keyword, the garbage collection is going to check for the next available memory location, which can fulfill your current memory requirement. So suppose customer is going to take 1 KB of memory space. It's going to go start looking in this section for 1 KB of contiguous memory. And when it finds it, it's going to give you that memory and it's going to um, start cataloging this information. All right, inside this catalog, it is going to say that this memory location right now is pointed by a variable named C. If you assign C to D, it is going to start pointing these two variables through this reference. And then unless these objects, they go out of scope of their current block, or they call a function called dispose, right? It is going to keep the count of this memory location as 2. Unless this goes to 0, this memory location will not be given to anybody else. Now, if the garbage, for performance reasons, garbage collection says that, hey, when I run out of space, I'm going to see which elements I cannot free up. And the ones that cannot be freed up, they are promoted to another segment of the garbage collection or the heap memory, and it is called as garbage collection generation 1. Now, there are 3 generations: generation 0, generation 1, and generation 2, right? Garbage collection generation 2. GC0 is the most volatile of all. This is where the maximum action is happening. So when you request memory, you're going to get it from this section. When you release memory, it is generally going to come out of this, right? And then garbage collection keeps the decision of where it wants to free up the memory to itself. You should not try to influence that. There is a method called gc dot, I'm forgetting the name, but then it kind of forces garbage collection, right? Run garbage collection, free garbage collection, something like this. And when that happens, everything that has the reference count of 0, they're going to get freed up and they're going to be returned back to the managed memory resources, right? So this is garbage collection for you, and the way you implement that in any application is because your application is going to use resources. Now I'm going to call it GC demo. And out of the 3 type of resources that we have seen, the network, the file, the hard drive, and the memory and RAM, garbage collection guarantees that we are only going to manage the RAM memory resource for you. All the other resources, they are kind of with their responsibility of the application itself. So we're going to create an application. We're going to add the run function to this. And then inside run function, we are going to create another object, but let's first wire this thing up. New app, and then I'm going to say app.run. All right, let's go ahead and create a class, and we're going to call it network interaction. You would want to connect to the internet and you would want to download some data. So let's add public void function download data. And then this function is going to do the difficult task of connecting to the internet and downloading data. Right, I'm not going to show that code to you here right now. But for this, you will have to create resources that are going to, like URL, that is going to connect to the internet. Another resource could be a database. When you connect to a database, you create resources that lie in the category of unmanaged resources. Now, this part of the memory is called managed memory, right? The code that we load through the intermediate language, it is called a managed code. Now, the reason it is called managed, because the memory requirement of these programs, it is getting managed by the .NET CLR. But then this, if you remember the diagram from previous session, the .NET CLR kind of sits here, right? Under .NET, we have the operating system, right? And .NET relies on the underlying operating system for accessing all the other resources. So the input-output devices, they are getting executed through the operating system. And then operating system is written in set of DLLs, and it could be running C and C++ native code. When you go in the native world, what you are dealing with is raw pointers. right? If you remember our discussion on microprocessors, a pointer is a memory location, and you have absolutely no control over how many objects are pointing it, right? Because you don't have that object, you don't know when the resource is going to get created and when the resource is going to get released back. To When you're dealing with native code like this, you give away the responsibility of freeing up that memory back to the operating system or back to the framework that is providing you that. So at least two such frameworks that I can think of is ADO.NET, which is going to connect to the database, and the um, entity framework core or entity framework. They are going to sit between the .NET and say a database, right? And then connecting to database requires internet activity, Ethernet LAN activities, and for accessing LAN, they will again have to go through the operating system, which means that they will be using pointers and unmanaged resources at some point. Now, when this transition happens, .NET promises that we are going to take care of all the managed resources, but then the unmanaged resources should be disposed of. And for that disposal, they recommend that we inherit from a class called iDisposable. Right? If I hit Control dot and say implement interface, it is going to give me one method called dispose. Right? Now, this dispose function is going to free up all the unmanaged resources. Another thing that we have to take care when this is happening, give me 1 second. Right. The application that is going to consume our network interaction is going to look like this. Network interaction, and it's going to be new network interaction like this. And then on this network interaction, you're going to call the download data function. Once we are done with this function, it is our responsibility that we dispose this particular object. But then remembering to call dispose function like this is tricky. And this dispose function then eventually is going to come here. It's going to free up all the unmanaged resources. But there is a way you can enforce this. One way is, so I'm going to show the try finally way first. Because network is very fickle, you don't know when the network is going to go down and when you are going to see the exception, right? And then when there are exceptions, you will need a try catch block. The catch block is going to take care of the network outage. It is going to probably gracefully handle that. But then the resources that were created, they have to be disposed. And you cannot dispose those resources in the catch block. You should not dispose those resources in the catch block. The right place for that disposal is in the finally block. Now, this becomes very tricky and very repetitive, and that's why we don't do it this way. The recommended way is you do not even create this object here like this. So you create a concrete type and you use something called as using over here, and you can move the entire object declaration to inside the using statement as well. So I'm going to create a variable in the using block using the var keyword and say new network interaction. And then I can do the download network interaction.download inside this using block. So this using block guarantees that the object that is created using the syntax, at the end of this using block, they are going to invoke the dispose function. And the responsibility of the dispose function is that it is going to free up the memory resources. There is only one problem with this. Right? When you call the dispose function, that function is already returned back to the free memory. And then you cannot free one memory location twice. So suppose that we got this blue box as an object, right? When we call the dispose function, we are going to the garbage collection is going to free up the resources because of the code that we are going to put here. But the garbage collection thread also has a copy of this, and it would come and it would free up this memory location once again. Because we don't want to free up the same memory location twice, we will have to call a function called suppress finalize. Right, and the function that I was trying to recollect over here, free and run, which is going to force garbage collection. Suppress finalize is going to take an object. So we're going to require an unmanaged object over here. So suppose I'm going to put an integer I here. This is not correct. I don't think it's going to take value of I. All right. This is a managed resource, a value type, but then the unmanaged resource that you create, say a network object, you're going to have to pass that object over here. And garbage collection would know that because the dispose is called, the resource is already freed. I am not going to free up that resource when the actual garbage collection thread runs. So this is the first step. To force garbage collection, you can do finalize, add memory allocate, collection count. All right, the object is gc.collect. All right, this is going to forcefully run the garbage collection. If you read through the documentation, it's going to say forces an immediate garbage collection of all the generations. But then the minute you start calling this function, and let's look at the other load as well. There's a number that you can pass 0, 1, and 2, which is going to select that specific generation and free up memory for you. But then the moment you start calling these functions yourself, you kind of start interfering with the garbage collection thread and ruin its strategy, the heuristic of freeing up memory when it feels that it is right. Right? So you can force garbage collection through collect. You can stop garbage collection on a specific object by calling gc.suppress finalize on this particular object. So the correct way of disposing has at least one more step, which is suppressing this thing. And because there are going to be other resources, you are also going to have to provide a destructor. Now, so far, we have only seen constructors, but then destructor, they have the same syntax as in C++. So with this destructor added, right, you will have other resources that you would want to free up. You can free up those resources inside this function. So once you take away the ability from the garbage collection that, hey, I'm going to dispose the object myself, you are going to have to take care of everything else. And then you probably wouldn't want to do it over here in this. You want to take away the entire activity of freeing up resources in another function, which is going to take a Boolean variable. So this function is going to be another void function. It's going to take Boolean, and that variable we're going to call disposing. Before you call the dispose function, so let me come back to this code again. The using statement is going to ensure that this function gets called. Right? This function has a responsibility of freeing up resources. Right? The managed and unmanaged resources, they're going to get freed up using this thing. But if the garbage collection thread runs before this dispose function is called, you would want to execute some form of control as to who is disposing what object. And if the disposal is happening through the garbage collection call and not a dispose call from a statement like this or a statement like this, then we would want to free up the resources, the unmanaged resources ourselves. And in that case, we are going to say that, hey, release only the unmanaged resources. And to control that, we are going to use this variable. Right. So using this variable, we're going to say that if it is disposing, we only release the managed resources, and managed resources, they are going to be object like a customer C assigned to new customer. Let's go ahead and create that class. Because we have provisioned a class, this particular object here is a managed resource. Let's assume that this is a pointer or a network related resource. So inside this function, we are going to dispose of only the managed resources. All right. So the variable C itself is going to get disposed here. And all the other unmanaged resources, they will still get disposed through this particular function. And when this function is getting called, it'll become our responsibility to call this thing. And to trigger that, we are going to pass the dispose function through here. All right. So when the using statement occurs, we are going to call another function which is going to dispose of the managed resources. We're going to suppress the resource finalize from the garbage collection on the unmanaged resources. And when all of this completes, we're just going to mark that our dispose activity is completed. And for that, we are going to use another flag. I'm going to call it disposed, assign it to true, and we're going to declare this value over here. Disposed, and it is false in the beginning. So we start with the private variable. We initialize it to false, and when this is false, it means that the managed resources, they have not been released. And via that, we're going to say that if this is coming through garbage collection, we don't want to execute your code. We want to wait for the dispose function getting called. The release of a function of an object which is using unmanaged resources should only happen through the dispose function. Right? There are multiple checks that we are going to implement. One check is going to be in the dispose function, which is disposing managed resources, but then this only happens when the object is not already disposed. Right? So it's a little complicated topic. If we come back to this diagram, we are going to have two types of resources. One is going to be a managed resource, but .NET CLR is going to take care of you. It sits in the code segment or the data segment. In the data segment, the unmanaged resources could be disk and file and network, which is going to get pointed by different type of object, like the one we're going to see in the Entity Framework core session. To dispose of the memory, you are going to have to inform the garbage collection thread that, hey, there is an unmanaged object that I have, and then I take the responsibility of freeing up that memory, right? And then because I'm freeing up part of the memory, I'm going to free up the managed resources as well. So the dispose function is going to release part of the object. The disposing function is going to release part of the object. All right, and that is what you'll have to do through the rdispose function. All right, so I'm going to share this code with you, and this is garbage collection, and this is rdisposable. All right, so that is the end of our session for today. If you guys have any questions, feel free to ask. I'm going to be around for another 10 minutes.